Hello, today I wanted to go ahead and demonstrate my HCI Wii project. This project had to do with demonstrating physics in the real world, kind of help kids to understand the equations of motion a little better. So this is the program I built. Put together. It was built on top of one of Johnny Lee's pre-existing programs. The basic thing that I took from Johnny Lee's website was the ability to track an infrared light using the Wiimote. From that, I added on a new GUI that allows one to visualize the position and velocity and the acceleration of the object that you drop. So that's the first part of the program. If you can see, this tab is where you'll be able to view the raw data. So this is basically going to be tit for tat, the data and the input that the Wii sees as the object is falling. From the position locations that are recorded by the Wiimote, then we can get the velocity at each point in the object's path, and we can also get the acceleration of the object at every point along its path. Now, of course, according to physics, the acceleration should be constant, and so we can check that with our little device here. So right here, this is our setup. This is the Wiimote right here, and this is the infrared light. The infrared light will project light over to this direction right here, over to against this wall. Since this wall is rough enough, then the light will scatter and won't reflect back towards the Wiimote. But if there's any kind of object that has reflective tape on it, then that surface will catch the infrared light from the lamp, and then the reflective tape will reflect the light directly back towards the Wiimote. And then the Wiimote will record the location of the object which is falling. Okay, so let's get started, and what our goal is to see how good the kinematic English equations actually predict the location, the velocity, and the acceleration of different types of objects. Okay, so let's get started. Let's run this program and see what we get. Oh, now first off, we're going to get an error message because I don't have my Wiimote connected via Bluetooth. So let's stop this. Now let me bring up my Bluetooth hardware devices. Double click on the Bluetooth adapter. Okay, so what we do is we press down on the 1 and 2 while we double click on this Nintendo Bluetooth detection. Okay. And as you can see, it detects the Wiimote, so we can put the Wiimote back in its place. Right there. Okay. And now we're ready to start our program. Okay, so here's our program. Let me zoom in. Okay, so we got that. These are the main buttons that we're going to be using. So clear displays is if this display ever gets too messy and you need to clear it. The first thing you need to do before you start your experiment is to calibrate your device so that you know how many pixels in this screen correlate to 1 foot. So depending on how far back you are away from the Wiimote, that'll change how many pixels there are per 1 foot. So let's go ahead and calibrate the Wiimote right now. Okay, so there's the Wiimote. I wish I could get the Wiimote and the calibration in the same picture, but I'm not going to be able to. Okay, now this is going to be 1 foot measurement, and this is where we're going to be dropping our objects. I'm going to go ahead and put a little marker on the floor so I know where we recorded. This little edge is going to be where I can drop my objects. Okay, and then I'm going to use this infrared. This is an infrared light. When I push it, when I turn it on, it will look like it's not on, but it actually is lighting up. just by the human eye, you cannot see the infrared actually light up, but you can actually view the infrared light via the camera. So the next thing we have to do is, let's push this calibrate button so we can start our calibration. Let's clear this first. Okay, push the calibrate button so we can calibrate 1 foot. And you have a little pop-up that pops up. Okay, now here's 1 foot. All right, now it says it's waiting for the second point. Okay, now we're going to get this. For the original program, it would need a third point, but there. All right, so the calibrations are now complete. Now we're ready to start our experiment. Let's get our calibrating device out of the way. All right, and here's the object that we're going to be throwing. This is our first test object. It's just a ball. It has several reflective, shiny, reflective safety tape on it. And this is stuff that you can get at Lowe's or Home Depot, whichever one. And so I just put some double-sided sticky tape on it and taped it around the ball. For most of the drops, it's always gonna reflect off of one, but I just put it, I don't know why I put it all around the ball, just so I can choose whichever side I want to throw with. Okay, so now we need to press the start stop recording experiment. So we push that. Okay, we are ready to start recording. Now for this, we don't use the infrared pin. We actually use the infrared light bulb because we want the light going away from, because we want the light that is projecting away from the Wiimote directly parallel to hit this object and shoot back to the Wiimote. So let me see if you can. Now let me give this a try. I hope I get this in the video camera. Okay, that was a good one. Now let's stop our recording experiment and see what we get. Let's review our results. Okay, so this is what our results look like. Let me zoom out. These are what our results look like. As you can see, this is the exact plot line that comes from the Wiimote, from what the Wiimote recorded. So here's that information. Here's the point position, the Y position versus the time position. This is the X position versus the Y position. So that's the same exact thing as this graph right here. The next one is the Y position versus time. And you want to do that because you want to see the Y position versus time relative to the velocity versus time and the acceleration versus time. Now if you can see the velocity and the acceleration, you have a lot of spikes in your data, and that's because the Wiimote is not ideal at collecting the points. Sometimes perhaps the light will reflect off the ball or the object falling, reflect off the reflective tape and bounce back to the Wiimote, and it might show, due to the direction the light is coming from, the Wiimote might think that the ball is in a different position than it really is. So it's not a perfect, or you might just have a data spike, or it could have gotten a reflection from 2 different points on the reflective tape. So it would look like the velocity was something that it's not, because the point data was from 2 different points on that bit of tape. So what I've added to this is a noise adjustment. Okay, we really, when it comes to velocity and acceleration, this is one thing that's really important to learn when you're recording data. When you're actually working with hardware that records telemetry data or any kind of engineering, is that sometimes more data is not always better. So if you can see right here, you can see a couple of lines or dots which are actually not perfect, don't quite fall into that perfect slope right there, and that's due to error in our telemetry collection device, i.e. the Wiimote and the reflective tape combination. So that is something that you have to take into account when you're doing any kind of engineering. So how do we fix this? We just eliminate some of the dots that we don't need. So, and you're like, well, how do we know which
dots to eliminate? Well, dots which are fairly close together can probably be spaced out or eliminated. See, these are very close together, and you can see there's an error right here. So one of those points either came from a different location on the reflective tape, or some other glitch occurred. So let's go back to our graphs. Now you'll notice this line is pure blue, this one's pure blue, this one's pure blue also. If you look at this graph right here, it's not pure blue. It is, this graph looks kind of purple, and that's because you have two plots right here. You have a blue line overlapping a red line, and what the red line is the pure data, or the plot with noise. So the red line is always going to look exactly like this plot right here. Now the blue line is the one that's going to change as we adjust the noise. So I guess I can't move that, but I'm going to click this noise button, minus sign, and you'll see the graph, the blue line, actually change. Every time I click the minus sign, it changes some. And you'll see if I click it too much, if I go too far, I've reached a maximum noise, which I've allowed, because I did some testing and realized that anything past an adjustment distance of 100 pixels, you get it starts getting rough. So I didn't allow anything higher than that. You get a rough estimate of what our true object paths look like. Let's just add back some of those points a little. Okay, it's getting better. It looks more like the line. We might want to have a few more points so that our line looks like the original data, just a little bit better. There, that's about good. This looks about right. Okay, so let me zoom out and show you what I've done. Okay, so if you see, the acceleration and the velocity graphs look a lot different now. I'll show you what all the graphs look like when I start adjusting the noise. So this is what the graphs look like originally when there was no adjustment to the data, to the recorded data. Okay, so we start filtering. You can see this right here is more than likely a spike in data, because you're not going to have a velocity that goes from like 3 to 13 in less than a second, especially when I'm dropping a ball. So and we still have a lot of points. And you can see this adjusting, and it still mimics our filtered line, still mimics the full data set, still mimics it pretty well. I'm going to stop right there because that's really good enough. So if you see, let's try this again. Let's see how well the kinematic equations are able to predict the velocity and the acceleration. And well, the acceleration is assumed to be a constant. So once we adjusted our line to the approximate to a good data set, then the kinematic equations use that adjusted data set, that cleaned up data set, to do its predictions. So it says it started out at approximately 4 feet per second, and then at 2.15 seconds, at 0.343 seconds, the velocity was 7. So let's see how that turned out. At 0.343, it was at 7. That's very true, approximately 7. And let's see what it says it was at 0.142. This is 0.14 is going to be in between here. So it says it's about at 3.47 velocity, and it's 4.9, so it's very, very close again. And that was the end of it. Let's see what the acceleration was. So it says the average acceleration, have it at 20, 27. It's supposed to be 32. Here's 32. So it kind of goes all over the place, the acceleration. But average, let me see, zoom adjust. I also have a zoom adjust, auto zoom. So the acceleration really should be constant. It should be a average of, it should be a 32 constant acceleration. And it gets this 32 in the middle of this. I guess you could take the average, but that's not really what you're supposed to do. It should show, it would be nice if it showed an average of, it would be nice if it showed a straight acceleration of 32. But anyway, so that is the program. As you can see, this was the actual velocity, and the kinematic equations did end up predicting the actual velocity fairly well. Let's try a different object, something that should completely fail the kinematic equations, should not be able to follow the kinematic equations at all. Like a piece of paper, something extremely light, the kinematic equations are supposed to be for a unit mass, or a point mass, I'm sorry, point, something very small, something that does not induce any drag. So let's find something that does induce drag and see how it does, how far it's off from the kinematic equations.